today there are two topics on tap. First, we're going to prove Toda's first theorem about the power of exact counting. And then we're going to get further into sharp P by studying a complete problem for it, the permanent. An excellent computational task. OK, so first thing is Toda's first theorem. And as I mentioned last time, it's that the polynomial time hierarchy is contained in this funny class, BPP to the parity P. OK, so if you have randomness and the ability to solve this parity P problem, like checking if a circuit has an odd number of satisfying assignments, then you can do all of the polynomial time hierarchy. And of course, I mean, this is like a weird, we have this parity P for proof purposes, but maybe it's easier to think of it as being contained in the bigger class BPP to the sharp P, the ability to exactly count the number of satisfying assignments to the circuit. And then we're going to prove that today. Toda's second theorem, which we'll prove later, basically de-randomizes this. So it gets that pH is contained in just P to the sharp P. Okay, so that really, says without randomness or anything, the ability to exactly count satisfying assignments is more powerful than anything in the polynomial time hierarchy. Great. So what are the ingredients for this proof? There's three of them for Toda 1. First one we proved last time. It's the Valiant-Vazirani theorem, which is originally about the complexity of unique SAT. So just to remind you, this means that it was a reduction from SAT. It was a randomized reduction to basically the unique SAT problem. And took a circuit and output like randomly a bunch of circuits such that this one was satisfiable if and only if one of these guys had a unique satisfying assignment. Of course, if you have a unique satisfying assignment, then you have an odd number of satisfying assignments. And so this implied that NP is a subset of RP, well, to the unique stats, I guess. But for the purposes of this proof of Toda, we're just going to remember two things. First of all, never mind about the one-sided error. We'll just allow ourselves two-sided error, because eventually when we get into the polynomial time hierarchy, there'll be like negation, so never mind the one-sided error. And we'll give ourselves this parity P oracle. Okay? Remember, if you trying to tell the difference between 0 satisfying assignments and 1, well, you can do that if you can tell the difference between even and odd. OK, so that's one ingredient. Second ingredient is on your homework. It's that parity P to the parity P is equal to parity P. And the proof of that is like some mucking around with non-deterministic Turing machines and some arithmetic mod 2. OK, but basically it's saying something like, if you have a non-deterministic Turing machine that can make calls to a parity P oracle, and nevertheless you want to know, does it have an even or odd number of accepting paths? Well, you can do that just in parity P by converting it to some oracle-free machine and asking if that oracle-free machine has an even and odd number of paths, accepting paths. And the final ingredient that we'll need is this theorem that we studied came up with when we were studying actually Arthur Merlin classes. The theorem that if NP is contained in BPP, then that implies the whole polynomial time hierarchy is contained in BPP. And if you recall, we originally proved something like this with just if NP is equal to P, then the polynomial time hierarchy is equal to P. That was sort of the original motivation of the polynomial time hierarchy, understanding like what you could do if you could solve NP efficiently. And we came to this by asking about the same question, but just allowing our notion of efficiency to include randomness. And we get the same theorem. You can solve NP efficiently with randomness, then you can solve the whole hierarchy efficiently with randomness. And that was we got proved that by mucking around with AM and MA. And it's not as easy as that fallacious oracle proof that I put on the piazza. It's very good you guys figured out the flaw in that argument. I'll partially put that there to remind you that this theorem actually takes a little bit of work. And secondly, to make you skeptical whenever I say anything about an oracle or oracles, it's always very fishy, so you should always be skeptical. Especially when I now say this fact, which is that this proof relativizes, meaning for any language A, if I just stick A here, it's still true. And I specifically emphasized that point when we proved this theorem. I don't know if you recall. It's actually easy. I mean, if you just remember the proof, it's all that business with there exists and for most and the backwards are, quantifiers and so forth, and the slashes. And then at the end, you had a deterministic verifier always. And on the left hand of the slash, it was about it equaling 1. And on the right hand, about equaling 0. And you just have to always give the oracle A to that verifier. And then just all the proofs you can repeat. So, have to take my word for it. OK. So these are all the ingredients we need. And now I'll prove Toda's first theorem. And this theorem I'm going to give is due to Fort now. The proof I'm going to give. It's not really so different than Toda's original proof, but somehow it's a bit cleaner. So here's the proof. First I'll write the way he writes the proof, and then I'm going to expand upon one part of it that is maybe not so clear. So the first thing that Fort now does is he says, well, this theorem, Valiant-Vazirani, also relativizes. Which is true, but eventually I'm going to let's look into that because I'm always a little nervous about these claims. So we're going to look into it, but let's just proceed from that. He says that this proof also relativizes. And therefore, from here to here, it's also true if you stick any oracle. So let's stick a parity P oracle and get that NP with a parity P oracle is a subset of BPP with a parity oracle, P oracle with another parity P oracle. Yeah, whatever that even means, you have to actually check that this is an associative operation, but don't worry about it too much because I'm going to drill into this in a second. But OK, if you accept this, then, well, this parity P oracle by part 2, this is equal to BPP to the parity P. And then, OK, now we're going to use the fact that this relativizes, and we're going to stick a parity P oracle everywhere here. And so we have the hypothesis. The hypothesis is literally true with the parity P oracle. NP to the parity P is a subset of BPP to the parity P. So we can therefore conclude that pH with the parity P oracle, really any class like sigma I class with the parity P oracle is a subset of BPP with the parity P oracle. This is by 3. And then we're done. Actually, we're better than done, right? Because OK, this definitely just contains good old pH with no oracle. And that's what we were trying to prove. OK, so it's a bit of a magic trick. But let's drill into this part because, he was really excited to write a 4-line proof of Toda's theorem, but it's worth maybe understanding what this means. This part I'm going to accept, though, that once you get that NP with the parity P oracle is a subset of BPP with the parity P oracle, then this is fine. OK, so yeah, let's spell this out. Instead of also literally trying to justify what is it, if I can relativize this proof or what does this even mean, let's just dig in a little to what's going on in the proof, and we'll just see that it's fine. OK, so let's literally try to prove this. So how do you do that? You say, well, let's let L be a language in this class and show that it's in this class. So let L be in NP to the, OK, and now I'm going to pick a particular parity P complete language. So that's odd sat, this classic parity complete language. Parity P is closed under many one reductions, so it suffices for me to use a complete language. OK, so what does that mean? So L is decided by a polynomial time non-deterministic Turing machine M with an O oracle. I'm going to stop writing odd sat. So O, I just mean the language odd sat. OK, in the sense that when X is in the language, this machine has at least one accepting branch, and when X is not in the language, all its branches are rejecting. But its computation is allowed to query this oracle. Okay, and now we want to decide L in BPP to the parity P. Okay. So we got to give an algorithm. So okay, given X, an input. The first thing we're going to do is use Cook-Levin. Okay, so we have this Turing machine M. It's like fixed constant size object. We got an input X, and I want to basically run Cook-Levin on it to create like a circuit sat version. Okay, so apply Cook-Levin, and what does that give you? Well, right, Cook-Levin just converts like the operation of this Turing machine into like an equivalent circuit, where like the non-deterministic bits that this Turing machine use are like the inputs to the circuit. Like X is actually fixed and hardwired into the circuit. It's like the starting configuration. It's like on the tape at the beginning. And you can imagine the Turing machine, non-deterministic Turing machine, takes its like non-deterministic bits as like an auxiliary input. So Cook-Levin would give you just a circuit like Cx, sort of a function of the non-deterministic bits, with the property that Cx is satisfiable if and only if X is in the language, because if and only if there are some non-deterministic choices that make M accept. Except it's not as easy as this, because M is not like a regular old, a plain non-deterministic Turing machine. It also has O oracle calls in it. So if you imagine like converting like the tableau, I guess, of like M's operation to a circuit, there's this weird like non-standard part where like it goes from like having something printed on its tape to in one step like getting the answer to whether or not that string is in the language O. So basically what that means is like you need to have a circuit, but not just any old circuit, a circuit with O gates. Okay, so you get a circuit, let me just write it like this. Okay, so we're imagining a circuit that has not just ands and ors and nuts, but also like, arbitrary fan-in like gate that like you fan in some bits, and it just outputs the answer to whether that string is in O. So write Cx, right, such that X is in L if and only if Cx is satisfiable. Does that seem okay? Okay. Okay, so now we're going to kind of recall a little how the proof of the Valiant-Vazirani theorem goes. In some sense, we're like checking that indeed Valiant-Vazirani is relativizable, but we're just going to do it explicitly. So we have the circuit. We want to know if it's satisfiable or not. So we're going to apply the Valiant-Vazirani proof, or idea. And what does that do? It considers all possible ranges, like 0, 1 to 2, 2 to 4, 4 to 8, 8 to 16, for how many satisfying assignments this circuit might have. For each one, it picks a hash function with an appropriate range of size about equal to its guess for the number of satisfying assignments. It builds the circuit that says, oh, like you satisfy the circuit C and you hash to all 0 string, and checks if those are, tries to imagine if those are uniquely satisfiable. So this like randomly produces a bunch of circuits, C1, C2, and so forth, some polynomially many of them. But now bear in mind that these things are also circuits with O gates, because you take C, which is a circuit with O gates, and like, okay, you put some hash function ANDed together with it, that's fine. But these are all like this weird circuit with O gates. Okay, and it has the property that if C is unsatisfiable, then these are all unsatisfiable. And if this is satisfiable, then like at least one of these will have exactly one satisfying assignment with high probability. Okay, so basically now this BPP to the parity P algorithm, which we're trying to give for L, needs to know, for each I, if Ci is, uniquely satisfiable or not satisfiable. Okay. And it's perfectly fine if it can tell whether CI has an odd number of satisfying assignments or an even number of satisfying assignments. Okay, you don't have to worry about what happens when it doesn't have 0 or 1. It's fine whatever answer you give in that case. You just need to make sure that like if it has 0, you say 0, and if it has 1, you understand that it's 1. So I can even cross this out and say like has an odd or even number of satisfying assignments. Okay, so now what's the problem we're facing? We have a circuit. We not only want to know if it has an even or odd number of satisfying assignments, but it's not just any old kind of circuit. It's a circuit with O gates in it. But this is horrible, but let me just go backwards here. Right, this kind of question, is the number of satisfying assignments for CI odd? This is like precisely parity P problem, parity P to the parity P problem. Right? You could solve this question in parity P to the parity P by just non-deterministically guessing all possible assignments here, and then you just have to check whether that assignment satisfies this circuit, which you can do with the help of a parity P oracle to answer all the O queries in the circuit. So this task that this BPP to the parity P algorithm has to do for each of these circuits is naturally in this class. What this is equal to this class. Okay, so this algorithm can solve all these questions with just a parity P oracle. So even P to the parity P can do it at this point. Okay, and that's the end of the proof. Okay, any questions about that? Yeah.
Can you just repeat the line about how your reasoning for why it's a parity P to the parity P problem?
Sure. So remember what this means. When are you in parity P? You're in parity P if there's a non-deterministic Turing machine such that whether or not it has an even or odd number of accepting computational branches determines the answer to the problem. Now, with a parity P oracle, it just means that as you're doing this computation, you're allowed to ask parity P queries. So the algorithm for solving this problem is, you use your non-deterministic branching at the beginning to guess or existentially try out all possible assignments to this circuit. And then if you could, then sort of deterministically determine if this circuit is satisfied or not, you would have established that answering this problem is just in parity P because, whether you get an even or odd number of answers exactly solves the problem. You can't quite do that because CI is not just like a normal circuit. It's like a normal circuit but with O gates in it. And so you have to figure out how to also figure out the answers to those O gate questions inside the circuit. But you can exactly do that if you're given a parity P oracle. You just need an O oracle. So you can evaluate all the O gates in the middle. Great.
Can you remind why parity P to parity P is equal to parity P?
I cannot. Good trick. Nice try. You almost got me there. Yeah. When I'm playing trivia with my brother, he always says oh, can you repeat the answer? And I'm yeah, that's good. It's on the homework. Okay. Hey, guess what? Congratulations. We're now exactly halfway through the class. We're halfway through the 14th lecture. That's halfway through the class. And that's good because I would now say that we've done a lot already, right? Here we are with parity P and sharp P. I think you know all the complexity classes now. If you're if I encounter a well-trained complexity theorist, I expect them to know what sharp P is, and I expect them to know what AM is. And now you guys know that. One second. On the other hand, you also know other ones like parity P and this truly obscure ones like S2P and BPP path. So any class you encounter in the future that you don't already know, you can be assured that it's an obscure class. So you don't have to feel bad about not knowing it. Actually, I thought that, but then I remember there's one more that you should probably know, which we haven't mentioned yet, which is This one, it's near and dear to my heart. BQP, it's problem solvable efficiently with a quantum computer. But we're not going to talk about it in this class. But now you know that one too, and so really you're done.
QMA. Don't you also need that one?
Obscure. Yeah. I know, yeah. Sorry, you TA'd a class about it, but yeah, Tom?
I just have a question about the notational trickery we did in the beginning with like NP, like VV relativizes, gives like NP with a parity P oracle, subset of VPP with a parity P oracle with a parity P oracle. Like, is it actually legit like parenthesize like when you add on another add on the other oracle, it gets attached to the other oracle? Like, does that even make sense?
Yeah, I mean, I think if you want to like actually make this notation make sense, you can. I think if you have a class to the like A to the B, does that even make sense? I think like maybe this should be a class. Basically, I think the correct meaning is that like this base class, like imagine this is like, I don't know, imagine this is like, I don't know, NP, and this is like, I don't know, something crazy, like parity P. Okay, like this means like this base class, it gets access to the B oracle and to this oracle. But that doesn't really help it because, I mean, under most normal circumstances, right, if the NP algorithm wants to ask a B oracle a question, it can like kind of ask it through this kind of oracle because like B is contained in this class. So like you can just imagine, so that I think proves that somehow like this notation is associative, like it doesn't matter if we write like this or something. Right. So this class makes sense, and then like this machine, this NP machine, can ask queries of languages in this class. And sort of in particular, it can also ask queries of languages in this class because this language is in this class. But instead of like trying to like define that, I was just like, well, let's just do the proof and we'll see it's okay. Yeah?
So like this seems like this is stronger than just putting the extra parity P on the outside because that is like literally the same as if you only have one. I guess if you have two oracles, one for one language and one for a different language, but they're the same class, that doesn't compute at all.
Right.
So.
Yeah, I mean the point here is that like you get to, in this algorithm, you get to even ask parity P to the parity P questions, which is what we eventually kind of saw here, right? Like you need to be able to do that. Right. Do you have a question?
This is always what, like, if we had P and next, like on the exam,
Yeah.
then maybe like it could happen that like the P machine can't even ask like such big queries. I don't know.
Yeah, I don't want to go out on a limit and say like this always makes sense. So that's why I'm always nervous about this stuff myself. So that's why, I mean, I wanted to write this and like it can be, one can make sense of this, but I thought it was simpler to just like literally make sense of it in this specific case. And yeah, the whole oracle notation actually does not make sense at all, because it does not make sense to like, theoretically this, like a class is a set of languages. And there's no meaning to like relativizing a set of languages. The only thing that you can relativize is a computational model. But somehow like we, identify the computational model with a set of languages decidable in that model. And it makes the notation bad. Okay, moving on from such horrible issues, let's talk about some pleasant issues like permanent. So we're going to study for a little while longer these two classes, which are friend classes, sharp P and P to the sharp P. This is a class of functions. This is an associated class of languages. And this is a beautiful class which complexity theorists enjoy studying, mainly because it has a complete problem, which is beautiful. And that complete problem, which is great, is the problem called the permanent, which I'll tell you about. Okay, and much in the way we kind of really love like the fact that there's a complete problem SAT for NP, which has like many nice properties. Like SAT is downward self-reducible and has this like search to decision reduction that we use several times, and like Karp-Lipton. It has lots of great properties. Permanent problem also has like many, many wonderful properties. which I'll just state here without even always saying what they even are. But we'll eventually see them all in this class. First of all, it's downward self-reducible. I'll remind you what that means shortly. It's also randomly self-reducible. This one we haven't seen before, and it's pretty great. This is like unlike SAT. This means you can reduce computing permanent to computing permanents on like smaller sized inputs. This one means you can reduce computing a permanent on a given input to the ability to compute permanent on like a random input. So it's some kind of like, in particular, that gives you some kind of like worst case hardness to average case hardness reduction, which is great. Shows that if it's hard to compute permanents on all inputs, then it's even hard to compute it on like most inputs. That's great. It also has something called an instance checker, which we're going to study later in this course. What else is great about it? Oh, it's not only complete for like sharp P, but it's also complete for like problems, or for like, well, let me just say for this class that the textbook calls algebraic MP, which is basically the analog of NP for arithmetic circuits. So we've been studying Boolean circuits. There's also arithmetic circuits we'll talk about later. There's like kind of an analog of NP for this class, and permanent is like complete for this class. So it's really great.
That's the same as VNP, right?
It's the same as VNP. And that textbook actually calls it alg NP/poly. The classical name for it is VNP, with V standing for Valiant. So alg NP is kind of a better name, but okay. Actually, let me write this over here because it's going to be the greatest thing for us. I will tell you, if you didn't already know, what the permanent is. It's a concept from linear algebra that's similar but different from the determinant. So the permanent of a matrix A, in this class it'll always be n by n matrices. Okay, it's the sum over all permutations of 1 through n of, now like you look at A1 sigma 1 times, these are entries of A2 sigma 2 times up to A n sigma n. Okay, or you could write this more briefly as products I goes from 1 to n of AI sigma I. Okay, and this, a permutation kind of is like a generalized diagonal, if you will. So like if you have some matrix, right, like these entries here are like, you kind of have to have like one entry from each per row and one entry per column. So like maybe this, this, this. It corresponds to the permutation where 1 goes to 1, 2 goes to 3, and 3 goes to 2. So you like go over all those things, you multiply the entries, and you add everything up. Yep?
If permanent is complete for these two different classes, does that mean alg P equals sharp P?
No, because it's like, sharp P is a class of functions from strings to integers, and alg P is like a function, it's a class of like formal polynomials in a sense. So they're just about different objects, and it's like a different notion of completeness. Yeah. I normally don't like to do these polls, but pardon me?
E to the sharp P is equal to E to the alg P?
Probably not. I have to think about that, but I think not. I normally don't like to take these polls, but like, I mean, do people like familiar, put up your hand if you've seen a formula like this, but like for the determinant? Okay, so good. So, and maybe you've even seen the permanent before. Great. So the determinant, I mean, like, you can compare this with the determinant. Some people define the determinant exactly like this, except that like right in here, it has a factor, which is like the sign of sigma, which is a group theoretic concept, but like it's some number that's plus or minus 1, depending on the nature of the permutation sigma. That's one way to define the determinant. There are other ways. It's pretty much the only way to define the permanent. Now, if you look at these two objects, the determinant and the permanent. It's very interesting to compare them. You might say, well, which one is harder to compute? And a naive person would say, well, it should be the permanent, right? Because like it's simpler. You don't have this like weirdo factor of plus or minus 1 that seems unnatural. But it turns out it's just the reverse. So the permanent is actually very hard to compute, and the determinant is not. So let's just, for simplicity, focus on matrices A with entries from the natural numbers. So the determinant is computable in P. Let me write FP because it's actually a function, but like there's a polynomial time algorithm that, given a matrix of integers, outputs the determinant. You studied that algorithm in linear algebra as an undergrad. Whereas the permanent, it's going to turn out, is sharp P complete. Okay, so it's basically, there's no efficient way to presumably compute it. And this is a famous theorem due to Valiant, less Valiant from 79. One thing, yeah.
So, as someone who hasn't seen the determinant before, does it have any like interesting like linear algebra interpretation corresponding to the determinant's interpretation?
I'll talk about this. It has fewer interpretations, sadly, but it has some similarities to the determinant, and it has some interpretations, but not as many as like the determinant's even more glorious in some sense. So yeah, let me say a few things about it. So in fact, if you like literally have to compute a permanent by hand, you can do this, but like somehow there's like a slightly, don't even want to say more efficient, but like there's a more natural way to do it by hand, which is this thing called like cofactor expansion, which you can also use. I mean, if you have to compute a determinant by hand that's like 3 by 3, you probably also use this algorithm. It's like you take like your favorite row or column. So maybe I'll take the top row, and like you go through it, and like let's say you're on 3. Then you kind of like cross out sort of temporarily this row and column, and like you take the permanent, recursively if you will, of this remaining 2 by 2 matrix, multiply it by 3, and then like add that up. So like the permanent over there is like 3 times the permanent of 5, 9, 6, 5. Plus 1 times the permanent of, here you like cross this one out and this one out, so it's 3, 4, 2, 5.
No, wait.
What?
You're going on the column. Sorry.
Well, I'm going on the rows. It's okay, you get the same answer if you go on the columns, but like I'll take 4, I'm going 3, 1, 4, and then I'll cross this one out and I get 1, 5, 2, 6. This is not very important.
No, if you go on the column, the second one should be plus 1 times the permanent of different thing.
Huh?
Yeah, I think you crossed out the middle row when you did the second one rather than the top row.
Yeah.
Oh, did I?
Yeah.
Oh, whoops. 1, 1, 9, 2, 5. Thank you. Thanks, Alex. Good. Okay, so that's one way to compute it. Okay, you're still not really done. I suppose you should, this one in turn is like 5 times, well, the permanent of 5 is just 5, and then plus 9 times the permanent of 6 is just 6. But you can recursively finish the job. You probably, hopefully, know the analogous method to solve the determinant is the same thing, except like when you're going across the row, you alternate signs. So like you do plus 3, minus 1, plus 4, and then minuses and so forth. So in permanent, you'd have a minus 1 here, but in permanent you don't. And just the correctness of this procedure just follows from the definition. I mean, if you just think about it for 1 minute, you'll see that this algorithm computes this sum. So if you think about that, I mean, what happened here? To compute the permanent or the determinant, you have like n recursive calls to like permanents on like n minus 1 by n minus 1 matrices. Okay, so this is not like efficient. Like if you were to branch this all out, there's like depth n, so it'd be like an n to the n time algorithm. But it's something. The reason I bring it up, though, is it does show that the permanent is downward self-reducible. Okay, which again means that like you can compute the permanent in polynomial on n by n matrices in polynomial time if you have an oracle for the permanent on n minus 1 by n minus 1 matrices. So if you have the ability to solve the same problem on smaller instances. And this is similar to like SAT, right? You can solve SAT in polynomial time on n variable instances if you have like an oracle that can solve it on n minus 1 variable instances. You just try x1, 1, or 0, call your oracle, and collate the results. Okay, so that's a good property of permanent, and we'll use it in a later theorem about the connection between de-randomization and circuit lower bounds in complexity theory. Right. Another property of the permanent is a minor one, but like it's unchanged if you swap two rows or columns. So let's say if you swap two rows or columns, you could easily verify that also from this definition. Determinant has a similar property, except it's not unchanged. You negate the answer if you swap them. But there's one glorious property that the determinant has that the permanent does not have, which is the determinant is also unchanged if you take one row and add it to another row. It does not change the determinant. It's just not true for permanent. And like that's the critical property about determinant. It's the thing that lets you do Gaussian elimination. So you can like take a matrix and like by suitably adding rows to other rows, you can like really simplify the matrix until it becomes diagonal, and then the determinant is easy to compute. So there's no Gaussian elimination or anything for the permanent, and like we don't really know any great way of computing it, and indeed it's as hard as sharp sat. Okay. So interpretations, like this permanent was invented like a million years ago in linear algebra, so why did it come up? Well, I'm not even actually that sure, but I'll tell you one like natural interpretation or meaning for it. It has this particular meaning when the matrix has entries that are 0 or 1. In that special case, it has a nice, very nice meaning. So let A be the 0, 1, I'll put it in quotes here for a second, adjacency matrix of a bipartite graph G on n plus n vertices. Okay, so it's a bipartite graph. I actually don't literally mean the adjacency matrix. I mean the matrix where you have a 1 in the ij entry if vertex I on the left is connected to vertex j on the right. So like the natural kind of object for a bipartite graph. Maybe I'll even draw a little example. So this is A. It's like 1, 1, 1, 1, 1, 1, 1, 0, 0. You can check if I did that right or not. And then I claim that the permanent of A is the number of perfect matchings in A, in G. Which is a very natural quantity. I mean, it's a natural concept. And why is that true? If you just look at the definition, right? Like a potential matching is the same as a permutation, right? It's like a map from the numbers 1 through n on the left to like distinct numbers 1 through n on the right. And like this is 0 unless all these entries are 1. So it's like it counts 0 unless you do indeed hit like a perfect matching that's in the graph. Okay, and for example, we can now infer that the permanent, at least the special case of the permanent problem with 0, 1 entries, is in sharp P. Remember, sharp P is the class of all counting problems where there's like a non-deterministic Turing machine whose number of accepting paths equals the answer. Okay, and that's, we can show that number of perfect matchings is in this class because your non-deterministic Turing machine, it just like existentially guesses a potential matching and then checks if it's really in there, in the graph. Okay, and then number of accepting branches is equal to the number of perfect matchings.
So does this mean that it's easy to compute the parity of the number of perfect matchings? If they use the permanent coincides with the determinant?
Yes, you've made an excellent observation. Which I was thinking about saving for later, but I'll mention it now. Yes, computing the permanent of any matrix, actually, mod 2, is in P, or FP. And, well, maybe you saw why, but do you see why? If you want to compute the permanent, mod 2, you just compute the determinant. And it's the same, because minus 1 is equal to 1 mod 2. So yeah, you can determine if a bipartite graph has an even or odd number of perfect matchings in polynomial time, which is cute. Yeah?
Same for almost any path? Or if you just took like the regular adjacency matrix?
Yeah. Yeah, it's like cycle covers, kind of. Cycle covers in a directed graph.
No, I mean if you take the actual adjacency matrix, not like the A, B thing.
Yeah. Maybe like.
Like you could solve the decision version then by like adding one.
Yeah, no, it's like it would give you like it's not quite Hamiltonian paths, right? It's like one factor is like covers of the vertices by paths and cycles, probably. Something like that. I'll let you work it out. Incidentally, there's a slightly more complicated result that shows that you can actually compute it mod any power of 2 in polynomial time. That requires some tricks. So permanent on 0, 1 matrices is in sharp P, and like actually Valiant proved the stronger result that just computing a permanent of 0, 1 matrices, or counting the number of perfect matchings in a bipartite graph, even that special case is sharp P complete. So I will prove this theorem in this course. It has 3 parts, the first part of which is somewhat painful. So the first and main part of the proof of this theorem is, well, it's a reduction. It's like showing that sharp 3 sat, given a 3 CNF, exactly counting the number of satisfying assignments, reduces to permanent on matrices with entries -1, 0, and 1. Okay, and I suppose this is like, yeah, let me just write it like this. Okay, so that actually shows that computing permanent on this special kind of matrices, all -1, 0, and 1 entries, is sharp P hard. That's pretty good already. But okay, we actually would be elegant to actually get this stronger result. This, by the way, we'll see later in the course. It's a straight up gadget reduction, but it's tricky. So it takes a little bit of time. Part 2 is, okay, if you have permanent on -1, 0, 1 valued matrices, there's a Turing reduction from this problem to permanent with non-negative entries, non-negative integer entries. Okay, so somehow you can convert it to an equivalent problem or be able to solve this problem if you can solve it with non-negative entries. And I'll show you that today. In fact, I'll show you 2 proofs of this today, because it illustrates how glorious the permanent is. And the third part, which I'll also show probably at the same time I show this, is the final reduction from permanent over non-negative entries. Actually, this is like a parsimonious reduction to permanent over 0, 1 matrices. Okay, so given a matrix with non-negative integer entries, you can just map it to a polynomially larger matrix with only 0, 1 entries, such that the 2 matrices have the same permanent. And that's not hard. I mean, it's also like a little gadget thing, but it's not hard. And incidentally, part 3 shows a nice fact that I kind of slipped over. This implies that the permanent on non-negative entry matrices is itself in sharp P. Because if you want to have a non-deterministic Turing machine whose number of accepting paths is equal to the permanent of this matrix, you just first do this transformation to a 0, 1 matrix, and then you count the number of bipartite perfect matchings in that matrix. That's kind of a quirk. I don't want to get overly enthusiastic about it. So for example, this problem cannot even be in sharp P. It doesn't even make sense because the answer could be negative. So there's no way this problem can be in sharp P. But I don't want to get overly excited about that fact. I mean, this shows that this problem is in quote unquote P to the sharp P. Say quote unquote, I should probably put FP because it's a function problem. But basically, I mean, it shows that you can also compute the permanent of matrices with positive and negative entries if you have the ability to, I don't know, solve sharp P. But if you really want to get technical, then like we even have this fact. Okay, so 1 is like a pretty tricky gadget reduction. 3 is like a not very hard gadget reduction. And 2 I'll show you a couple proofs of because it's nice. Okay, so 2 proofs. They illustrate like nice properties of the permanent. 2. So here's a problem. Like you've got, what are we trying to do in 2? Let's say you kind of have the ability to compute the permanent on like non-negative entry matrices. And but now you have this like matrix with plus or minus 1 and zeros in it. How are you going to compute it? Okay, so proof 1. This is modular arithmetic. Okay, and this one's kind of nice in that it works, doesn't have to be plus or minus 1 and 0. It just works for any integer matrix. So let's say you have A, and it's an integer matrix, n by n. And imagine it's the entry to the input to a problem. And so its entries are also written down with like bits. So let's say its entries are L-bit integers. Okay, so every entry is like an integer between plus or minus 2 to the L. Okay, so that like input size of the problem actually is, like n squared times L. So one thing I want to kind of do before we get started in this proof is ask ourselves, like, how big could the answer be? So actually, can somebody tell me like a reasonable upper bound on the magnitude of the answer?
Factorial times 2 to the ln.
Very good. N factorial times 2 to the ln. And why? Well, if you just, even look at the definition, there's like n factorial sum n's. And each one in magnitude, this is at most 2 to the L, at most 2 to the L. They're all at most 2 to the L. You multiply n of them together, it's at most 2 to the L times n. Okay? And that's good because, like, the number of bits you need to write this down. Let's call this number q. To write, something at most, like log of q, which is, n log n plus ln. Okay, so this is a number of bits, which is, linear actually, or, at most linear in the input size. Okay, so at least it's good. You're not trying to like write down something that's impossibly long. That's a side benefit. Okay, but let's get back to the proof. Here's the trick in the proof. You know the answer is going to be at most this q. The trick is you just try to compute, or you just imagine what is the permanent of A modulo, we say 10q. And if you think about it for a second, if you could know, what I want to say is if you could know the answer to this question, then you could know the answer to the real question you want to answer, which is just literally what is the permanent of A. And why is that? Well, here's the number line. Here's 0. We know that like the true answer is between minus q and q. So we're trying to find out the real permanent of A. Maybe it's here. I'm just saying, compute it modulo 10q. Okay, so if it's between 0 and q, that means like nothing happens. If it's between like minus 1 and minus q, then like it kind of will go to here, right? This interval kind of gets mapped to this interval. Okay, so if you compute it correctly mod 10q, you either get something in here, and then you're like, okay, well, I know the answer is positive that number. If you get something up here, the answer is actually 10q minus your answer. Okay? So this thing determines what you really want to know. It's permanent of A if that's greater than or equal to 0, and it's 10q minus permanent of A if answer is less than 0. Okay, you can.
Oh.
Wait, what?
That's fine.
Yeah, I think it's okay. Okay, of course you can like compute q and stuff yourself. So I'm just trying to say if you can compute this, then you're done. Okay. And yeah, that's going to be easy. suffice it to compute this. Remember what is the scenario here. Like the scenario is that we're kind of sad because we have this matrix with potentially negative entries, and we're only imagining, we're trying to do this reduction, so we're only imagining we know how to compute permanence when you have non-negative entries. So what should you do?
Just add 10Q to all the integers.
Yeah. That's right, yeah. So just replace all the negative entries of A with equivalent non-negative ones, where equivalent means mod 10Q. In fact, I guess Q is very large, so you can literally just add Q to them, and then that'll make them non-negative. The point is that this does not change the answer. Let's call this, let's say, forming A prime. And by the nature of modular arithmetic, like the permanent of A prime, it's congruent to the permanent of A mod 10Q. Because the permanent is just defined with like addition and multiplication. This is what you want. So great. So now compute the permanent of A prime, not mod anything, just compute it. Exactly, over the integers.
Over natural.
Yeah, over natural. Sorry, yeah, okay, good. Over naturals, thank you. Which is the thing that you're reducing to. It's the thing we're assuming you can do. And you get a number. I mean, one good thing to point out is like the entries of A prime are just numbers at most q, so they're also expressible in like polynomially many bits. So we haven't really blown up the size of the instance. So we can do this with our oracle, and then we just reduce the answer mod 10q. Okay.
I think it should be plus. It doesn't matter, but like it's 10Q plus permanent.
Thank you. It does matter. Yeah.
Yeah.
Good. Good. Yeah, so we even showed, I guess what did we show? We showed that this thing is kind of like in FP, if you will, to the perm, and even with just one call to the oracle. Great.
Extracting like the original answer from the problem because you don't know what sign it is.
So first I claim that we can compute this number. Do you agree with that?
Yeah.
Okay, so that'll be a number that's somewhere between 0 and 10q. And it'll actually either be between 0 and q, or it will be between 9q and 10q. And then those two cases tell you whether the true answer that you're shooting for over the integers is positive or negative. Yep?
We assume that all the entries are L-bit ins. I like assume that this also works if you have like some entries that are really big and some entries that are small. So like.
Yeah, I meant less than or equal to L bits, yeah.
But I mean, then the size of your input is not n squared L if you have some entries that are really big.
Okay, so like let L be the maximum length of an entry in bits. That's what L should be, and then this is all true. And the input size is at least L plus, it's probably at least L plus n squared.
Yeah.
Yeah.
Which is, I guess, still a bit.
Okay, so like,
L is poly n, so.
I suppose it doesn't have to be, right? You could like have an input that's like a 2x2 matrix with like a billion digit integers. So I guess the correct thing to say, like to get it exactly right, is, well, what I said. So first of all, let L be the maximum length of in bits of an entry. This is not really right, but it depends how you define the problem. You can define it so that they have to be L-bit integers, but like even in the most liberal way of defining the problem, the input size is at least L plus n squared. So you got to write down that longest thing, and you got to write down like something for each entry of the matrix. And then this upper bound is still polynomial in this bound. Yeah, that's good. Yeah, so maybe it's not linear in that sense. Like maybe this could be like quadratic or something. Okay, so that's proof 1, which is very nice. Let me do proof 2 of this. So I'm going to reduce, again, computing permanence with -1, 0, and 1 entries to non-negative entries. And I'll do a different proof that sort of maybe only directly works in this case where you have -1 is your only kind of negative entry, which is fine for Valiant's theorem. And this proof also has the advantage that it's somehow more efficient, but it's not really a big deal. But it also illustrates another nice property of the permanence. Probably its most important property. It's proof 2 by interpolation. Okay, so let's say we're given A, and now, as I said, I'm going to assume it really is just -1, 0, and +1 entries. Okay, and we imagine we have the ability to solve permanence on non-negative matrices. So what do we do? Okay, we got these pesky -1s in our matrix. We're sad about that. So let's replace, sort of in our mind, all the -1s with x's. And what is x? It's an indeterminate. Okay, forming A sub x. So there's a matrix whose entries are 0, 1, and a symbol x. Now what is the permanent, algebraically, of AX? Well, you can write it, put it into this formula. Some of these guys are 0, some of them are 1, some of them are x's. So it's a polynomial in x. It's a univariate polynomial. It's just x. Actually, with, I guess, non-negative integer coefficients, but I don't care that much. In x of degree at most n. This is really the ultimate glorious property of the permanent. It's a polynomial. It's a multilinear polynomial in all of its entries of A of degree at most n. So it's like a low degree polynomial. I'm not saying like write this, the algorithm writes this down or anything. We're just imagining this so far. But people agree with this? So call it P of x. Okay. So, all right, from the algorithm's perspective, there's this mystery polynomial P of x that it's very interested in. So here's the point. Given P of x, given an oracle for computing permanent on non-negative entries, see, the algorithm can compute P of x for any non-negative x of its choice. Right? If it has like some number like 5, it wants to know P of 5, it basically just replaces all the -1s in the matrix with 5s. And then now it's a non-negative matrix, and it says, okay, oracle, what's the permanent of this guy? So it can do it for any non-negative x's. So like, let's say it does it. So do it for, I don't know, x equals 0, 1, 2, up to little n. Make n calls to the oracle. And now check it out, right? Like, this is x. P of x is some polynomial of degree n, I don't know. And we just learned its values. We learned this height, this height, this height, this height, this height, etc. Learned this height. We learned all these n plus 1 values. But okay, you know, right? This is some elementary stuff. This is like n plus 1 points. It's a degree n polynomial. So it uniquely determines the polynomial. Yep.
So this even works for integers, right?
Yeah. I mean, it works if like all of the negative numbers are the same number.
Could you replace -n with nx?
Pardon me?
Could you replace -n with nx? And then
With nx?
times x.
Oh, yeah, that's good. That's a good observation. Yep, that's fine. So yeah, if you had like, the observation was if you had like a bunch of different negative entries, replace all the -1s by x, replace all the -2s by, in your head, 2 times x, all the 3s by 3 times x, and so forth. And this trick will work. So that's good. Okay, but anyway, to finish this trick by, use, Lagrange interpolation or whatever, to now literally determine p of x, like p of x's coefficients. So now the algorithm interpolates and like literally knows p of x explicitly. Okay, and then just output p of -1. All right, so then like now that you know the polynomial, you can figure out this. Well, let's say it was like this. So it's a pretty good trick. Yep. Yep.
Interpolating polynomial down explicitly, do you need to like bound the size of broken interpolation?
Yeah, that's a good question. The question was like, if you're writing down this interpolating polynomial explicitly, do you need to bound the size of the coefficients? Well, one thing we saw is that the answer to the permanent can be written down with a number of bits. That's polynomial in the entries, the size of the matrix. So we're given like a matrix with some entries, and then we're changing some entries to like n's or something, which is fine. That's like log n bits. So we saw before with the q and everything that like the answers we'll get back will be polynomial length. Like the number of bits to write down the answers will be almost polynomial in the input size. And then you kind of, I guess, need to know that like Lagrange interpolation is a polynomial time algorithm. So not just that like, it requires a polynomial number of arithmetic steps, but actually the numbers that are generated can all be computed in polynomial time and therefore have polynomial length. But that's true. Actually, okay, I'm sure it's true, but I just have to think about like one thing, right? Like one thing that's funny is that when you do Lagrange interpolation, like you enter into the rational numbers because you have to divide by things. It's funny because even though you know the answer in the end is going to be an integer, we have to be a little bit careful, right? Like if you have like, let's say n rational numbers, all with like different denominators, and like you add them up, the common denominator is going to be a lot bigger. I guess it's fine though. It's still.
Like the common denominator here.
Yeah, it's less than the product. Yeah.
Because this is what you divide by.
Yeah. So it is fine. But I mean, basically, yeah, you have to accept or remember that why it's indeed true that even when you're counting like bit complexity, Lagrange interpolation is polynomial time. But that is true.
Why did you say that this is more efficient?
It's more efficient in the sense that
Call n oracles, right?
but the numbers that you construct are smaller. Like you only call, it depends, it's more efficient in one way. I got this from some paper I was looking at. What you call the oracle on uses smaller numbers in this case. You only use like very small numbers, like up to like n, to like call the oracle. Whereas in the other case, you like call the oracle with like numbers that were as big as 10q, which is very large. So if you're really concerned about like how long does it take to compute permanent on matrices with entries that are this many bits long, you get a more efficient reduction this way. So like I saw this trick in like a paper that was really about like the exponential time hypothesis for like counting problems. Like if you imagine you can solve the permanent on natural numbers and like 2 to the little of n time, does that mean you can solve the permanent on -1, 0, 1 matrices and like 2 to the little of n time? So it matters if that n blows up to like n squared or not. But it's true, this one required n calls, whereas n plus 1 calls, where the other one required 1 call. Okay. Great. So that's 2 different ways to solve that one problem that arises in Valiant's theorem, how to get rid of negative entries in your computing permanents. And this second proof leads into like another glorious property of the permanent, which is the last one I'll tell you about. which is that the permanent problem is not just downward self-reducible, but it's also randomly self-reducible. Okay, so what do I mean by that? For this little story, I'm actually going to focus on a third setting of where the numbers come from. I'm going to focus on computing a permanent of n by n matrices over a finite field. For all the entries of a finite field, let's say for simplicity, just the integers mod p. Okay, you can do it over any field. And I'm going to also assume that p is bigger than n plus 1. So think of it as a large finite field. Okay. And part of the reason for that is it's going to be like there's a very natural way to imagine picking a random matrix over a finite field. It's not so clear how you pick like a random matrix over the integers. Okay, so here's the theorem. Let me write it on the next board. This is proved by Lipton in 91, and maybe also by Don Beaver and Joan Feigenbaum in 1990. Okay, so suppose there exists an algorithm or an oracle, whatever, O, that computes the permanent correctly on most inputs. On most inputs. Specifically, I mean this. Probability, if you take a totally random matrix from ZP with entries from ZP, the probability that O computes its permanent correctly is, now I'm going to write something that's pretty big, but like minus 1 over 3n. Okay, so you don't have to be able to compute the permanent perfectly. You just have to be able to compute it with high probability, where your error probability is at most 1 over 3n. But this is not the error probability of like the algorithm's random coins. It's over a random input. That's something we haven't talked about really in this course at all. Sort of average case hardness. Okay? Then, the permanent is in BPP to the O. What do I mean by this? I mean in the worst case. So you can compute correctly on all inputs. Now it's randomized, so there's a failure probability. The failure probability is only with respect to the algorithm's coins only. Okay, so there's a little bit of a subtle point, but it's important to understand what we mean. You start with an algorithm that's like good on most inputs. It computes the correct answer on most inputs. You convert it to an algorithm that's correct on all inputs. Well, there's a catch. The algorithm has a small chance of failing, but like its failure has nothing to do with the input. For every input, it has like a 99% chance of giving the right answer. Whereas here, there's like some inputs where like you definitely get the wrong answer every time you call the oracle. Do you catch the difference? So this is called worst case to average case reduction. And it's kind of cool because it shows something that it's very rare in complexity to see this. This is a worst case to average case reduction. It means, for example, suppose you believe it's hard to compute permanent in the worst case. Like have an algorithm that efficiently computes it for every input. That's the sort of thing we believe. That's like saying we imagine that p to the sharp p is not the same as p, basically. Or that sharp p is not contained in fp. Then you actually get a distribution on inputs where it's hard to be correct just with respect to that distribution with high probability. And it's a natural one too. It says that if you believe that, then you also have to accept that it's hard to compute a permanent with high probability over a randomly chosen matrix. And this is quite in contradiction to, let's say, SAT and NP, right? So let's say we believe that NP does not equal NP, does not equal P. That means, we don't think there's any polynomial time algorithm that works correctly to decide satisfiability from every formula. we really don't know a similar statement about, a probability distribution on formulas. Like, doesn't tell us anything like there's some natural way to pick random 3CNF formulas such that we also believe it's hard to get the answer right for most of these formulas under this distribution. We don't know any result like that. But we have that kind of result for sharp P due to some glorious property of the permanent. And that's very useful in complexity theory. Just remark number 2, this 1 minus 1 over 3n, you can get it down to be half plus epsilon. But it requires some more sophistication. Okay.
Epsilon is like any weight.
Yeah. You could probably make a subconstant too, but honestly I don't quite know the details. Okay. And the proof of this is not hard. It's similar to the proof we just saw about getting rid of minuses. Perhaps you could even guess it. Okay, so let's say you're given any A. Okay, you have to get the right answer on this matrix about its permanent with high probability. So what do? You try to reduce this computation to the computation of like a random permanent. Because you're good at computing randomly chosen, permanents of randomly chosen matrices. But it can't just be any totally random one. It has to have something to do with A. Otherwise, what are you getting? So this is what you do. Pick a random matrix R, a uniformly random matrix R. Okay, and now here's the only trick. Let B sub x denote A plus x times R. Again, think of x as like an indeterminate. This is matrix addition and scalar multiplication. Key point is that, like, if you look at, let's say, B1, it's uniformly random. Right? Because you start with like a totally non-random matrix, but then to each entry you add, a uniformly random element of ZP. So basically, no matter where you start, it like uniformly randomizes it. And also same with B2. Right? You're taking an arbitrary, each entry is like some deterministic thing plus twice a random number. And like, 2 is invertible mod P. So I mean, adding twice a random number is mod P is the same as just adding a random number mod P. And similarly, B3 and so forth. These are all uniformly random in ZP to the n times n. They're certainly not independent, definitely not independent, but they're all individually, marginally, uniformly random. There's one more, B0. B0 is not uniformly random. B0 is just A. But, well, that's going to be useful for us too. Okay. So let's again let P of x in our heads or mentally be the permanent of B of x. And maybe I'll keep that up. Again, the key fact is P of x is a polynomial in x, a univariate polynomial, of degree at most n. So why? If you look at the definition, right? Oh, it's no longer there. Too bad. Each entry of B of x is a linear expression in x. Okay, so when you look at those like products of like the n entries of Bx, it's like products of n linear expressions in x. So it's a degree n polynomial in x. Great. Okay, so now this star observation, this is like another observation. Star implies that the probability if you pick x uniformly at random from from 1 through p minus 1, that O applied to Bx does not equal p of x, is at most 1 over 3n. Yeah, because when you do this, the matrix you generate is uniformly random. And thus the guarantee we have.
Should that be the randomness like for fixed x and random r or something?
Yeah, wait a minute. Maybe I've got this wrong.
Because the randomness.
Good, yeah.
Like the random thing.
Thank you. This is not right. Yeah. Thank you. Good. Okay, so in particular, right, the probability over R that O of B, let me write it like this, A does not equal P of A for any A between 1 and P minus 1 is at most n plus 1 over 3n by union bound. And this is about 1/3. So with high probability over your choice of R, you get the correct answer.
I mean, you can only, that's only if like P minus 1 equals exactly n, right? I mean, if P minus 1 is like n to the 100 or something, it's much more likely. But like you only.
Thank you, yeah, I'm really kind of messing this up. This should be n plus 1.
Yeah.
Thank you. Staggering across the finish line here. Good, thank you. Okay, good. So with high probability over R, you get n plus 1 correct pairs. You know, 1 P of 1, 2 P of 2, up to n plus 1 P of n plus 1. Okay, and now you're similarly done. So in that case, you would like interpolate. Well, in any case, you interpolate and get P of x. And you get the coefficients correctly with high probability, and then you output P of 0. Which with high probability is the permanent of B0, which is permanent of A. Okay, any questions about that? Yeah?
If you assume 1/2 minus plus epsilon, do you do some like coding trick?
Yeah, use coding theory is the trick. Okay, great. So next time, I haven't quite decided if I'll do Valiant's proof of Sharpie hardness, or I might switch to talking about a little bit about arithmetic circuit complexity. So we'll do one of those two things. We'll do them both eventually, but we'll see next time.